Most people treat track gauge as just a simple measurement, but that assumption misses the huge influence it has on a railway and the trains that travel on it. It's a dimension that quietly influences how fast trains can run, how stable they are at speed, and how tight the railway itself can curve. It even affects how track is maintained and whether different railways can connect to each other at all. So, if gauge has this much influence over how a railway works, why does it vary so massively across the world? This single measurement has a huge impact on the day-to-day running of any railway around the world. But how does it do that? It starts at the interaction between train and track, at the point where they meet. That contact point between the railhead and the train wheel is at the very heart of how a railway functions. It's here that the secret of how trains navigate curves comes into play, despite having no steering wheel at all. The behaviour at this interface places limits on how trains can be designed. The interface, and the track gauge that helps define it, places constraints on how large trains can be, and where their mass can safely sit. A train's size and centre of gravity play a major role in how stable it is at speed. This has direct implications for both safety and passenger comfort. And those same constraints don't just affect the trains themselves. They also limit how tight the curves can be, which in turn influences how the alignment of the track is designed and how a railway can be routed through the landscape. When a single dimension carries this many consequences, how it's defined and measured really matters. But what is this simple but hugely influential measurement? The one that underpins all of those limitations. Track gauge is the distance between the two rails on which the train wheels run. More precisely, it's measured between the inside faces of the running rails, taken at a defined point below the top of the railhead. In the UK, that reference point is set at 14mm below the head of the rail. That level of precision matters because even small changes at the wheel-rail interface can have disproportionate effects on how the railway behaves. So we've talked about what track gauge is and why defining it precisely matters, but achieving that measurement and keeping it where it needs to be depends on the physical components that make up the track. I've put together a track components ID guide that walks through those parts and explains how they work together as a system. It's free to download and you'll find the link in the description. If this measurement affects behaviour and design this much, you might expect it to be the same everywhere, but it isn't. Different parts of the world settled on different gauges because they were solving different problems. Broadly speaking, these choices fall into three main families: narrow gauge, standard gauge, and broad gauge. Standard gauge, which sits at 1435mm, is what much of the world now uses. It isn't standard because it's perfect. It's a compromise that works reasonably well across a wide range of conditions and across many different use cases. Narrow gauge railways use anything below standard gauge. They're often found in mountains or highly constrained terrain, where railways need to follow tight alignments and have more frequent curves. Narrower spacing of the rails allows tighter curves and lighter structures, making routes through difficult landscapes more practical, typically at the cost of lower speeds and smaller trains. At the other end of the scale is broad gauge, where the distance between the rails is greater than standard gauge. These systems tend to favour stability and capacity, supporting larger trains and smoother high-speed running at the cost of heavier and more expensive infrastructure. The key point is that none of these choices are inherently right or wrong. Each reflects local priorities, terrain, traffic type, cost, and performance. And once a gauge is chosen, those trade-offs quickly become locked in, shaping everything that follows. Those choices make sense within a single railway, but when different networks meet, their differences become a problem. That problem is known as a break of gauge. It can occur at national borders, or where legacy networks meet newer lines built to a different gauge. When trains meet a track of a different gauge, they can't just carry on and run straight through. Either the bogies on the train have to be changed, or passengers and freight have to be transferred to a different train. Both options are time-consuming, introduce delays, and add additional operational cost. In a world where railways are increasingly interconnected, those delays and added costs can quickly become significant. Within the EU, for example, there's a push to adopt standard gauge on new lines to improve interoperability across national borders. There are, however, some ways of overcoming the issue of differing gauges. One option is dual gauge, where 3 or 4 rails are laid in the same track to allow trains of different gauges to use the same route. It works, but typically only over limited sections. Dual gauge track is expensive to build and brings added complexity when it comes to maintenance, particularly of signalling systems. Another approach is variable gauge systems, where the wheels of the train can slide along the axle as the train passes through a specially designed installation, allowing it to change gauge safely. These systems rely on specially designed rolling stock and dedicated infrastructure. And this is where gauge stops becoming just a design choice. Once it's set, it becomes something the entire railway has to live with. A gauge measurement may be chosen after considering the needs of a particular railway system, but once that dimension is set and installed, it quickly becomes a constraint, one that everything else has to be designed around. Why is that? Because so many other things are then designed, purchased and operated around it. First and foremost, there are the trains themselves, and they're not cheap. Once a fleet of trains, coaches and wagons have been built for a particular gauge, a huge amount of capital is then locked in. Changing gauge would mean replacing or heavily modifying that entire fleet. And it doesn't stop there. Maintenance equipment, safety standards, and even spare parts and supply chains are all developed around that same gauge, with specialist machinery and components put in place to support it over decades of operation. The result is that changing gauge after the fact becomes enormously expensive and hugely disruptive. It's not something that can be done gradually or piecemeal either. Given the public role of railways in most countries, changing gauge would also require significant political will to push through the disruption it would cause. Ultimately, the decision on gauge has and will outlive the engineers who make it, continuing to shape how the railway operates long into the future. Track gauge is often described as just a measurement between the two rails. In reality, it's far more than that. It's a decision made right at the start of designing a railway system, one that goes on to shape train design, maintenance, speed, stability, and passenger comfort. And once that decision is made, it's one of the hardest things to change. So while gauge might look like a small detail, it's one of the most influential choices a railway ever makes, one that will last for generations.